His research focuses on computational generation and screening of porous materials for energy applications and modeling the self-assembly processes of metal organic frameworks, understanding ion transport in polymeric systems, and development of software for enhanced sampling techniques. His talk today will be navigating the landscape of advanced materials. Let's welcome Dr. Colón.
All right, thank you, Dr. Zipper, for the introduction. Thank you to NV Energy for the invitation and everybody for being here. So I'll just jump right into it with just the acknowledgements first, right? The people who actually do the work. This is my group picture we took, you know, just before the start of fall semester, where we could be outside and do things. And the picture needs some updating, but that's okay. So the work that I'll be presenting on today has been done by my student Krishnendu Mukherjee and my postdoc Sanosh. And then I have collaborators here at Notre Dame, Professor Luo, Professor Dowling, who talked to us a little bit before, Professor Felipe Herrera from the University of Santiago de Chile. And of course, I'd like to acknowledge CRC, so my work is computational. Without their support and their resources, you know, we wouldn't be able to do very much. And of course, NV Energy, right, so I was actually a student here at Notre Dame. I graduated in 2009. I was a SLAT fellow then. And now I have, you know, multiple undergraduate students who've had the opportunity to be SLAT fellows. Krishnendu was also an Isomers, right? So NV Energy has been a very important and big part of the research efforts that we've had, you know, really throughout my career. So I'm an assistant professor and I'm, you know, relatively new, so it is always a good idea to sort of give a sense of what your group does, right? So we do computational modeling with focus on materials. Porous materials in particular is an area of expertise, so we're looking at things like materials for the water energy nexus, right? So this is the process of how much energy do you require to produce clean energy, right? How much energy do you need to go the other way around, right? So how much water is involved in energy processes, how much energy do you need to produce clean water? I don't focus quite as much on liquid. I actually focus more on water vapor. So I'm really interested in, like, how do you capture water directly from air and produce then potable water? How do you do separations in the presence of water vapor? So carbon capture, right, is really important. All those streams contain water vapor. There's interactions there that are important. How can we control those? And then we're also interested in sort of this hybrid systems. You have soft matter, you have porous systems as well. So you can have very rigid, solidly, when it's sort of rigid and non-deformable porous cages that are connected by very flexible systems, where you form these now amorphous systems so you can expand and contract, and these things can then sort of respond to the presence of different absorbates. So you can think of sensing, capture, destruction, and so on. Looking at self-assembly of porous materials, so this involves research at different time and length scales, all the way from how do you form the fundamental units to transitions over to crystalline systems, so how do you terminate these and calculating those free energies. Then we're interested in other applications where we're looking at materials for quantum enhanced technologies, so that is a brand new area. I'm going to talk a little bit about that today. Looking at also ionic liquids for rare earth element separation. So this is actually a project funded by the DOE and in collaboration with Professor Ed McGinn. And then another thing I'm going to be talking about today, looking at machine learning for predicting absorption, right? So the idea that we can use machine learning not just to make new predictions, but actually tell us how do we intelligently navigate our space, right? So you have temperature, pressure, all these different variables that you can control when you're doing either experiments or simulations. How can machine learning help us be smart about which actual experiments to do and which simulations to do? So we're really motivated by this idea of the fourth industrial revolution, right? So steam in the 1780s, electricity in the 1870s, IT 1970s. And so now with, right, you saw, you know, VR systems, we got our Fitbits, we got, right, this continuous interconnection between technology and even our own bodies in many ways. Some people believe we're actually living in the fourth industrial revolution. We're about to begin one. right? And so when we think about that, so let's start from that premise. Well, then what does the future hold, right? What is the future of energy? What is the future of the environment, of health, of infrastructure? And you start thinking about those technologies that we want to develop to live in that future, you realize very quickly that the foundation of that is really advanced materials, right? So advanced materials are really the ones that are going to allow us to make that future happen, whether it be sort of new catalytic membranes to produce drinking water, right? Advanced materials that do, advanced diagnostics or drug delivery, and et cetera, et cetera. Okay, so this is where we lie, right? So we want to find those materials. So do they already exist? Okay, and we just need to apply them in a new context that we didn't know about? Or can we first discover them on the computer and then go then to the lab and make them and test them? Okay. So in our field, where we deal with metal organic frameworks, which I'll talk about in a little bit, this is more or less sort of what that workflow looks like for the modern computational materials design and discovery. We usually have some database of structures, which then you sort of simplify to what we call descriptors or features, and then you do some training and testing and validation. Okay, so how do you generate these databases? How do you quickly screen through them? Okay, how do you evaluate them? There's a lot of data that needs to go into this, but then there's a lot of applications that we're interested in that are very expensive. Okay, maybe very resource intensive. So maybe we don't have access to all of that data to then sort of leverage all the powerful things that we can do with machine learning. So what do we do there? So that's one of the areas where we are working on, which is essentially then also how do you produce this high fidelity data set, right? That's how do you get your data, okay? And then in new applications, right, developing the tools to just start to to begin to now evaluate materials in these new sort of technological settings that we're interested in. Okay, so I'm going to tell you a little bit, a quick story on us. A project very near and dear to my heart, something that we continue to do today, but this is mostly for my PhD work, and that is hydrogen storage, okay, using MOFs or hydrogen storage. So I mentioned MOFs now a couple of times. What are these? Are metal organic frameworks. The idea is these are comprised of inorganic nodes, organic linkers, and they're going to self-assemble in solution to produce a porous crystalline system. Okay, so now you have all these pores available to you to do reactions, to do adsorptions, separations, all these things, and you can actually then functionalize those organic linkers to add even more sort of tailorability to those, right? So you can imagine the library of these building blocks is huge, right? Let me just give you a quick sense. So this is a very small subset, and you can get a real sense of the diversity of structures that you can make with this, right? So you have things like H+1, which is a copper pattern wheel, and self-assembles with a benzene tricarboxylate to form these three-dimensional structures, and you have this pore here that have mostly the benzenes exposed. You have this little cage here with mostly the coppers exposed. You have different chemical environments within that. You have others that are like this, have a very tight window leading into a very large pore, so you can think of like almost molecular sieving, right? To do separations, you have one-dimensional channels, also that have then exposed metal sites to that, so you can do down chemical reactions there, right? And so the idea is we have a very rich then space, and we can now engineer these materials with, if we're smart about which building blocks we pick, to now get a desired material, okay? So that's where then sort of these ideas of computational high throughput screening come into play. If we take advantage of that modular nature of those materials, right? So combining inorganic nodes, organic linkers, we can be smart about it and do algorithms that then generate very large libraries of these structures. Okay, but then we need to characterize them. So what are their sort of physical properties? What is their pore size? What is their surface area? Right, are there exposed metals, things like that? And then can we quickly evaluate them for the particular applications that we have in mind? Okay, and so this, through these processes, we can get sort of plots that look like this, so to give you a very nice sense of what that structural property landscape looks like, so you can say, okay, the materials that I'm interested in are within these ranges of the physical properties, and those relate them back to these other structures. So the story of hydrogen storage is not a new one. It's sort of resurging now with the new administration in terms of the hydrogen economy. So that was, a bit before it's coming back again. And so the DOE has certain targets that they want for certain vehicular type applications. So they want 7 weight percent, 70 grams per liter, certain pressures and then temperatures. The idea is, well, those numbers really come from the energetic content that hydrogen has that would drive you sort of a similar distance as you would in a normal type of gas. Right, so that's where those numbers come from. And so here you get a sense of, right, if you just take hydrogen, you compress it to 200 bar, that sounds safe. This is the size of your fuel tank relative to your mid-sized vehicle. Right, so clearly that's not very practical, right? So then figuring out ways how we can sort of condense that to get the same amount of energetic content is important. When we think about storage, a lot of people we're beginning to think, oh, we just need something that interacts very strongly and has a lot of it inside. And that's not quite true, right? If you have something, right, so this is what we'll call an isotope, so how much you have absorbed versus pressure. If you have something that interacts very strongly, you're going to saturate very quickly. But then some pressure needs to be left over in your tank. You just can't just go to vacuum. You're not going to get all of it back. So really the amount that you are able to deliver is actually very small compared to maybe another material that doesn't interact quite as strongly, but is still able to get high capacity. So really, the engineering constraint is about how much gas can you deliver, not necessarily how much you can absorb. Right, so those are some of the things that we're thinking about when we're doing these types of studies. Okay. Our workhorse is Grand Canonical Monte Carlo simulations. Right? So Grand Canonical stands for Statistical Mechanics Ensemble, which means we fix chemical potential, volume, and temperature. And so the number of molecules is allowed to fluctuate, right? So I can put this material here in gray is my MOF, put this in equilibrium with a reservoir. And then once this converges, I can get how much absorption I have. Okay? And so we've been doing this for a very long time, and we show that we have actually very good agreement with experiments. So here the black line of the experiment, and each one of these open symbols is a separate GCMC simulation. Okay? And so here's hydrogen absorption at 77 K, and then absorption at room temperature. Okay, so we can get very good agreement between the simulations and the experiments, right? So that's always an important question that we want to be able to address. Okay, so with that, now that we, once we have then this sort of workflow established where we know we can get accurate simulations, we know how to do it, then we get into this idea of high throughput. How do we do this so that we can really explore these material landscapes? So here I'm plotting the deliverable volumetric, deliverable gravimetric hydrogen at 77 Kelvin and 100 bar. Each one of these points is a separate structure. So there's, in this case, there's over 13,000 structures that we evaluated. And then here we're comparing to what would be the sort of the bulk density of hydrogen in a compressed hydrogen gas tank. So here immediately we have sort of a very rich landscape of materials that outperform, right, that compressed hydrogen gas tank. In particular, we were really interested in these cyan colored structures, this SHG topology, so these are just different topologies of the crystals. We were interested because at the time, there was only one structure with that topology. It's a very rare topology, it's a very rare thing to find. And so through our algorithms, we were able to discover this new structure that had never been made. And then we went into the lab and actually then tested it, our predictions against the experiments, and found actually really good agreement. Right, so this whole idea is like, oh, really, like, can you find something on the computer and then like go and make it? Yes, the answer is yes, and we've been doing this now for quite a long time. Long time being, over 5 years, right? That's what a long time now is, right? Right, but you can go into the computer, right, do this sort of large-scale, high-throughput screening studies, discover new materials, and then go into the lab and produce them. Okay? So now that we can do sort of these studies where we have a lot of data, machine learning then comes into play, right? Really, the power of machine learning lies in the amount of data that we have. And so with Professor Luo, we trained some neural networks to make some predictions about precisely hydrogen storage. And then we started to think like, well, what about those places where we don't have as much data? Right? What about those places where maybe even the simulations are really difficult and really hard? Can we come up with ways in which we can leverage really the knowledge of the space where we have the data, where it's easy to obtain, and use that knowledge to make predictions in this new space where maybe it's really hard to make simulations or experiments. And so we do so doing transfer learning. So the idea is you train a neural network with your features in the system, so this volumetric surface area, gravimetric, void fraction, right? So how much empty space do you have in your system, the sizes of your pores. And we can do then that normal training using all of that data. And then when we want to make new predictions on a space where we maybe don't have as much data, we fix all of that, all those parameters that we found, and we just let the last couple of parameters move around, okay? And so what that has allowed us to do is we take, right, so all those 13,000 structures, okay? And so we have all the data, we validate it against just using 100. Okay, so I can take one space, I train it on all 13,000, and I take that knowledge, and I produce a new model that I train only using 100 data points. Right, so orders of magnitude less data, and I still get great agreement. Okay, so we were able to do it, say hydrogen at one temperature and pressure. We were able to transfer that knowledge to a different temperature, right? So maybe, right, this is something you want to do. Changing temperatures in your equipment might be difficult, right? So we can get great agreement there. And then beyond just temperature, transferring knowledge to a different adsorbate altogether. So now we do from hydrogen to methane, right? So it's a different structure, different chemistry altogether. We are able to also do that transfer knowledge. Again, just training that model with just 100 data points, just you doing that last layer, also, we're still able to get very good agreement, okay? Now, it doesn't always work, okay? The features that you use, right? So what are those parameters you're going to input to your model are really important. Okay, so we can do sort of feature analysis. We can look at hydrogen, right, and the different conditions, and methane. We see that, look, the features that are important are the same throughout. If you try to now do that transfer into a space where the features are different, or the importance of those features is different, you're not going to get very good results. Okay, so there's a limitation to what we can do. Okay, but if you have a good sense that your features are going to be similar, transfer learning can really be an important tool. Okay, so then after that, we were thinking, it's like, okay, you know, so here transfer learning, we found its limitations. Can we think about, can we automate this simulation process, right? I don't want to sit down and have to do all these 13,000 structures. I don't want to sit down and have to do, you know, however many hundreds of points I need for any given sort of temperature pressure landscape. So can I automate this in any way? And the answer is yes. And we're going to do that doing what's called sequential design or active learning. Okay. So the idea is we're going to have some sort of seed data. Okay, we're going to do some transformations, and then we're going to train it using what's called a Gaussian process. What's really neat about these is that it gives me a prediction, but it also gives me an uncertainty associated with those predictions. Okay, so what does that mean? So the model is telling me, look, I'm really confident about these points here. I'm not so confident about these other points here that I'm predicting. So great. Now me, as the modeler, I can make decisions as to where to simulate next. So let's go to those points where you're not as confident. And we can automate that process. So I can find where that maximum uncertainty is. I have some threshold. If I still haven't met it, I just feed back in and I keep going, okay? And so what we've been able to find now is that using this type of procedure, I can also save orders of magnitude in terms of the data required to develop these models. And so let me show you how this works. So doing methane, right? So here my solid points are sort of that seed data. And sort of these red points here are the predictions and the associated uncertainties, okay? So I look at my data and say, look, this is my maximum uncertainty point. That's where I'm going to simulate next. And so the model goes there, and then now does a molecular simulation there, and now my model changes. This is my new model, right? So boom, completely changed, but the uncertainties also go down. This is my next point, and then now my model changes again, right? So now with this total 1, 2, 3, 4, 5 points, I can get a really accurate model compared to that ground truth, to the actual simulations, okay? So this was just for an isotherm, right? So an isotherm means I'm keeping temperature constant, right? So I'm just doing one temperature. I can also simultaneously navigate temperature and pressure. And so that's what we show here. Okay, so I can show you here how my error, my predicted error is changing as a function of iterations. So it's about 33 iterations, and this is then sort of the mean relative error compared to that ground truth, which is under 1%. What does that mean? With 33 simulations, I'm able to make the predictions just as accurate, essentially, as almost 5,000 data points. Okay. So now this represents significant resource savings from the simulation side, but there's nothing that limits this to just simulations. This could also represent experiments. Okay, so this is really the power of active learning, where we now automatically select that next simulation and are able to save then significant resources. Okay, so now, right, so that gives us a sense of how we can reduce that so data requirements for these machine learning models. We also need to worry about sort of coming up with new ways to now evaluate materials in new settings of technology. Right, so here we're looking at entangled photon pairs for quantum enhanced technologies. Okay. So this is a paper that came out recently where they show they can actually do photonic quantum technologies in a chip. And so the idea is light comes in, you have this ring resonator, which is down where your photon entanglement takes place, and then you can come back and do a detector. And so this is key for quantum computing, cryptography, metrology, et cetera, et cetera. But really what allows you to do that is the material, right? There's actually a very limited number of materials that have this capability to have nonlinear optics. And MOS is one of those classes of material. So in order to expand in that material set that is able to do that, we need to now come up with ways to evaluate them computationally, right? And the reason why computation is really important in this case is actually getting single crystals for these systems is really difficult. You really need single crystals to be able to test them experimentally, right? So if you don't have single crystals, your signals, you're going to get something less than what would be ideal, right? So if it's really difficult then to get these single crystals, we want to make sure that when we spend that effort, we do so intelligently, okay? So we have, from literature, we have some idea of what are going to be some good properties for the materials. So things like chiral ligands, large dipoles, C10 metals, and non-centrosymmetric are going to give rise to these nonlinear optic properties. It's called spontaneous parametric down conversion, when one photon comes in, two come out, and this conjugate process is called second harmonic generation, where two photons come in and one comes out. Okay. So this is what we envisioned. So we're going to have a laser, it's going to pump into our material, and then it's going to produce those entangled photons. Okay, so now the challenge is, right, there's a lot of really neat physics that describes the properties of entangled photons. We need to link those physics back to the material. And the way we do so is using periodic DFT calculations that allow us to calculate what's called the Selmayr equations. This is the information about the refractive index and the second order susceptibility, nonlinear optics. And so these then two terms here are what give me the properties of those photons. Okay, so I'm able to now link directly the properties of the material to the properties of the photon. Okay, and we do so by integrating these types of equations, where again we imagine photons coming in through some crystal them off, and the two photons are going to come out. So the things that I'm interested in is how tall is this going to be, and how wide. Okay, so those are the properties of the photons that I'm interested in. Okay, but again, being able to connect that back directly to the material is really the challenge, and we've been able to do that. And so we took these three structures that were synthesized at the University of Santiago de Chile. Again, validation is really important, so we're able to make some calculations about what's called a phase matching angle, then the effective, and we get very good agreement between experiments and simulations. Okay? And so now that gives us confidence that the predictions that we're making about these structures are actually going to be accurate. Okay, so now that we have this, then now, right, we've developed a multi-scale methodology to evaluate these materials in this new technology setting. How can we come in now with these active learning processes to now help us explore these landscapes? Okay, so with that, I hope I've convinced you that computer simulations and molecular modeling are an important tool moving forward for materials evaluation in all sorts of applications, including hydrogen storage and others that have led directly to materials discovery transfer learning and active learning to help us reduce that data required in machine learning, and doing multi-scale methodologies for the evaluations in quantum technologies. So with that, thank you for your attention. I'm happy to take any questions.
With a lot of MOFs, like with gas storage, you have a lot of like dynamic behavior, like breathing and stuff like that. Is that something this approach can model? Because I know that's quite challenging because your material itself is changing during your process.
Right. So if you have a model that is able to capture that, the answer is yes.
Okay.
But then there's that big if, right? So if your force field is able to capture that dynamic behavior, that's still a big question. We're working on some of those things as well, so that gets back to sort of how do you even produce that high fidelity data set to begin with and developing those tools to do so. If you have that, there's nothing that prevents active learning from operating in that space.
Thanks.
Yeah.
So you mentioned that you were able to predict a compound that had the SHE topology and actually sort of synthesize that and show that it works sort of in the real world. Is it possible to extend these methods to predict new topologies in general that are actually synthetically accessible, or do you have to kind of a priori know, okay, we want this topology, what things make this topology?
So making new topologies, so that's a math question, and I think those have been enumerated. And then you're now just limited by the chemistry. So the way that we generate these is we think of the topologies themselves as a three-dimensional puzzle, where now my pieces are going to be the chemistry. And so I can match sort of, literally place it and rotate it until they fit, or maybe I need to, force it in there a little bit and do some other things. Discovering new topologies with this, I think that's more difficult. But if you have the topology, then this can work. We're also not limited to just topologies. It can be any network. So we're not necessarily limited to crystal topologies. If you have an amorphous network, then you have a good sense of where things are placed, then we can map chemistry onto that and do that in the subsequent relaxations.
Going back to thinking about your absorption isotherms and the model for that, we make a lot of absorbance for these emerging contaminants in my lab, and we're making isotherms, and it's a pain.
Yeah.
It's a lot of experimentation, so something like this can be useful, but what if you don't, so you have all the parameters that go into porosity, surface area, whatever, et cetera. What if you don't know what impacts the absorption? Where do you start there from a computational perspective?
Right, so, so where you need to know the features of your system is if you want to do some of these neural networks and things. The active learning doesn't depend on that at all. So it's completely blind to what the features of your material are. It just tells you where to test next and develops a surrogate model that fits to those points. Okay, so there you don't need necessarily information about your system to be able to say, okay, I just need some points here, the low pressure, couple of the high pressure, and I'm done. And I can get something that looks like a line mirror or something like that. Yeah, so you don't need to know necessarily anything about your system to do active learning. If you want to make predictions a priori about your system where you don't know sort of porosity or things like that, then you will need to train a new model already with, and then you get back into that stuff like, I need a lot of data, I need a lot of things, so that's a more difficult task. So consistency is one of them. It means so from a simulations perspective, it means that you have enough data to train a machine learning model, and that data, where it comes from, is something reliable. So your force fields are reliable, the way that you monitor your material is reliable, right? So my high fidelity data set, for instance, wouldn't include right now materials that have dynamic breathing, right? Because I can't capture that in my models yet, right? So that's what we mean by that high fidelity data.
So on both ends, basically. When I say both ends, I mean experimental data that's consistent, but also a model that can.
That's right. Yeah, exactly. Yeah. So the way I think about my molecular simulations I'm just running an experiment. I have some models associated, but it's still a computational experiment. In many ways, I'm trying to imitate what is done in the lab just on the computer, as long as I have the proper models to do so.
So when you come to the AI side, right, then I'm sure you have to intervene at multiple steps and introduce some physics-based insights into, to sort of massage it into where you want to go, right?
So for the active learning, I don't. The only thing that I'm intervening is I am performing the simulation the AI is telling me to perform. That's it. I'm not, like, I can literally set this up on a batch thing, submit it to the supercomputer, come back, I don't know, 6 hours later, depending on simulations, and I have these models all completely done. I don't have to intervene at all.
So when you do the, for example, the structure topology optimization,
Sure.
so in that case, it just...
Right, so there is not AI.
Yeah.
There is, I have a library of things, of chemistry that I know, right? So I know coordination environment, right? I know, right, a zinc, oh, so the zinc is going to be tetrahedral, or a carbon atom is going to be tetrahedral, and so I can be intelligent about which pieces I'm trying to match where. So there, yes.
Yeah.
Yeah, for sure. Yeah, but there, you know, I just have a library, and then I just need to mix and match.
Yeah,
this one
then
up.
when you go towards designing materials with the properties that you need,
Mhm.
using that particular factor, and then introducing AI, when do you depart completely from that realm of physics-based insights, and then you get into a space which is now AI, machine learning, Bayesian optimization thrown in, and then so that's always been my sort of confusion, because many times the system starts, I would say, diverging or whatever. Then you say, hey, behaving somewhat badly, we should introduce some practice or whatever based knowledge into it.
Right. So in our case, when we're doing just the act of learning, the model, so if it tries to make a prediction, we choose to do something there, and the model isn't fitting the data that we're trying to fit it in, the model recognizes that. It immediately says, okay, now I didn't recognize it before, but now I do. I have a lot of uncertainty there. And so we'll tell you to feed it that physics-based intuition that you want. So in my case, it's another simulation in that space so it can self-correct. Right? So having that loop where it's going to decide which data to come in and uses again that data to refit and learn what the model should be, that I think that helps to close the loop to avoid as possible the scenario that you just described.
Thank you.
All right, let's thank our speakers.